right in. So like Petra mentioned, my PhD work is using data collected during the Tracer Cubic Field Campaign, or the mouthful that is Tracking Aerosol Convection Interactions Experiment, Coastal Urban Boundary Layer Interactions with Convection. This campaign took place in Houston, Texas from June 1st to September 25th of last year, and the main hypothesis that drove this specific campaign is that complex interactions between sea breeze and urban circulations affect the planetary boundary layer, or PBL, and ultimately result in highly variable flow both spatially and temporally. There are many cubic objectives and goals to work towards, which you can see some examples of here on the slide, but for the sake of the work that I've been working on most recently, we'll focus on the final bullet with the goal of characterizing the sea breeze and its impacts on the evolution of the PBL structure throughout Houston. So in order to study and investigate the PBL, 3 mobile profiling units were deployed throughout the greater Houston area. OU-NSSL's Collaborative Lower Atmospheric Mobile Profiling Systems, or CLAMPS, and the University of Wisconsin's Space, Science, and Engineering Center Portable Atmospheric Research Center, or SPARC, were used to collect thermodynamic and kinematic data of the lowest few kilometers of the atmosphere. These systems included a halo Doppler lidar, an atmospheric emitted Radiance interferometer, and with the CLAMPS units, there were also microwave radiometers. The figures on the right-hand side depict some of these instruments and profiling units as they were deployed in Houston. The figure on the left-hand side depicts the locations of each instrument platform. The systems were spread through Houston in a way that creates a transect through the city, and in which led, in each location, a chance to sample different PBL environments. CLAMPS 2 was located at the University of Houston's Coastal Center and acted as the coastal observation site for the campaign. SPARC was located at the main DOE ARMS site in Pearland, Texas, which was south of downtown Houston, and this provided more of a rural/suburban location for observations. And finally, CLAMPS1 was located at the Aldine, Texas site, which was north of downtown Houston, and this site provided a more urban type of landscape and was surrounded by more urban structures. So with any scientific study, you always have to know why you're doing it in the first place. Tracer cubic data collection specifically helped to fill the gaps in some of the boundary layer observations for the summertime period. Obviously, one summer's worth of data isn't representative to every year's possibility of conditions, but it at least helps us to fill some of the gaps in our knowledge, and especially in regards to characteristics within the PBL under different conditions that are really often experienced throughout Houston in the summer. Additionally, sea breeze characteristics and trends are currently poorly understood, especially in complex places like Houston, where you have a large metropolis area really close to the coast, and you have several sources of different types of air pollution. The propagation inland, the sea breeze depth, and the effects on atmospheric variables and convection are just a few of the things that we don't fully understand, and we hope to address with this project. Finally, there are a lot of sea breeze research projects out there, but a lot of them rely solely on numerical weather prediction models. So this project was able to provide observational data to go alongside what we see with our numerical simulations. So to give a little bit of a sea breeze 101, along this important coastal area, sea breeze circulations often develop, which act to equilibrate the interface between the continental boundary layer and the marine boundary layers. The sea breeze circulation forms as the land heats up after sunrise, which we know is going to heat the air above the land faster than what you see with the air above the water, which results in rising motions and the development of a lower pressure over land. As a result of this rising motion and lower pressure development at the surface, we see a pressure gradient force form, which leads to the formation of an onshore flow and a sea breeze front, which you can see depicted in this figure here. This onshore flow brings cooler, more moist and stable air from over the ocean inland, which is depicted again by the sea breeze front. And since we all know that mass conservation is a thing, there is a return flow that is created above this sea breeze front, and it has the flow going from over land back over the ocean. This air tends to sink and it closes off the circulation. As the sea breeze front pushes itself inland, there is areas of enhanced convergence that can occur, and these areas of enhanced convergence can help play a role in inducing convection initiation as well. So one of the challenges of this project is identifying the sea breeze. We can see it pretty clearly when we're there in person. If you've ever been to Florida during the day, you can see it pretty clearly, but actually nailing down sea breeze cases and their timing was one of the biggest challenges I've had so far. So currently I have identified sea breeze cases using a multiple observation approach. Radar animations of the lowest tilt of the radar reflectivity from Houston's operational WSR-88D were created for each day of the campaign. A subjective analysis of these observations was completed to identify cases in which the sea breeze formed, which you can see an example of in the figures here on the right-hand side. In addition to this, the second step was to look at our observations, specifically our lidar observations. So when we look at our lidar observations, there are a few common signatures that we see on most of the sea breeze days. This includes an increase in the wind speeds at the time of the sea breeze passage, a shift to a southeasterly direction of the winds, and most often a decrease in the magnitude and time scales of our vertical velocities that we capture. Along with this, we also look at some surface meteorological observations from the two CLAMPS sites, and you can also see a rapid jump in the relative humidity, as well as a drop in temperature at that time of the sea breeze passage. So just to give a little example of some of the different campaign data that we have, we had a total of roughly 110 out of 116 days of really good data collection. Unfortunately, there are some data outages that are intermittent throughout the campaign because Houston's very hot and instruments don't like heat. So you do have some times where data outages do occur, but for the most part, we have a really great data set to look at. In addition to overheating instruments, oftentimes at CLAMPS2, we do have overnight outages with our lidar because fog would form on the lens. So out of all of this, there are lots of different phenomenon as well as sea breeze cases, and this is just a few examples. We had a lot of days with nocturnal low-level jets. We have land breezes or urban circulations, interesting signatures that we can pick up with our lidar especially, and also multiple distinct aerosol layers in the overnight period that are interesting for somebody to look at and maybe try to figure out, as well as our sea breezes. So now that the general overview information has been gone through, we'll get into the brunt of what I've been working on most recently, which is investigating the PBL heights, and specifically the PBL height prior to and after sea breeze passage. The PBL height is a challenge to estimate with several different instruments and methods that are currently used to try to detect it. People have used instruments such as radiosondes, ceilometers, space and ground-based profiling systems in order to try to detect the planetary boundary layer height. An example of some different results from radiosonde-based detection methods is shown in the figure on the left. And the really big takeaway here is that these different types of methods can result in very different height estimates. Whether you are looking for the maximum of a potential temperature gradient or humidity gradient, or the different heights of different temperature inversions, these can lead to very different results, whether you're using radiosondes or other types of instruments. One big thing to also keep in mind is that the planetary boundary layer height is not always equal to your mixed layer height. So some of the different methods are actually finding your mixed layer height, not just the boundary layer height. And in general, when you have convective environments, especially during the daytime, the mixed layer height is a pretty good estimate of boundary layer height, but in stable or overnight conditions, that's not always the case. So it's good to know what your target is before you choose what method to find the boundary layer height. So the approach that we use to find the planetary boundary layer height is utilizing our dynamic and thermodynamic profiling data that we collected and passing this data through a fuzzy logic algorithm. The use of fuzzy logic allows for a measure of truth to be applied to the data rather than just your normal binary yes-no thresholding. This algorithm was created by Dr. Smith and Carlin, and it expands on the work of Bonin et al. 2018, in which he only used lidar measurements to find, along with the fuzzy logic method, to find the planetary boundary layer heights. So the addition of thermodynamic data can help the accuracy of the algorithm during periods, especially around transition periods, and when temperature inversions have a greater impact on the planetary boundary layer heights. These thermodynamic data and the method used also help to ensure that the found boundary layer height estimations are staying connected to the surface, which is a key distinction between the boundary layer height and the mixed layer height. This specific approach uses a two-step approach. The first step involves the use of measurements of mixing, so think vertical velocity variance or the height of a temperature inversion to determine the first guess PBL height estimates. The second step uses indicators that mixing has actually occurred, like a signal-to-noise ratio or constant wind speeds within a layer to give a second estimate of the heights. As I mentioned, this is just a visual example of what the first step is looking at. One of the inputs used in this step is the vertical velocity variance, which you can see an example of here from CLAMPS1 on July 17th of last year. Membership functions are then applied to this input data and aggregates are found. And these aggregates are basically the weighted mean values of the fuzzified objects and values. After this first set of input data, the first height from the bottom at which the aggregate value is less than or equal to 0.5 is the first guessed estimate of our planetary boundary layer height. The 0.5 value is used to ensure that the height found is still connected to the surface. We then are able to go into our second step, which is using the indicators that mixing are found. At this step, discrete Haar wavelet transforms are used to detect gradients in fields like the signal-to-noise ratio and temperature. The second step of the process produces estimated planetary boundary layer heights a lot like the first, and you can see the comparison of the two estimates here. This second step acts more as a refinement of the estimated heights from the first step, and a triangle mean is then applied to these second generations that you see here to smooth the heights and the second step, and that is the final project of our estimated boundary layer heights. There's a lot of complex mathy things happening there, but that's a general overview of how it works. So once the PBL height algorithm was applied to each site for every day of the campaign, I moved forward into a more Seabreeze-specific analysis. I'm currently working to gain insight into the general effects of the sea breeze on the planetary boundary layer heights and how the sea breeze affects the thermodynamic characteristics of the boundary layer. My first step has been to apply some composite analysis techniques to each site. I'm using the thermodynamic retrieval data from the TROPOE retrievals applied to the AERI and microwave radiometer data. These retrievals are formed using an optimal estimation method, which you can learn more about in the site and the works that are cited here. The retrievals are in 10-minute averaged profiles with no additional smoothing currently applied. To create the composites, I first found the sea breeze passage time, currently based off of 100-meter lidar observations. The composites are 4-hour windows with 2 hours prior to the sea breeze passage and 2 hours after the sea breeze passage. The results I'm showing here are preliminary and do not include proper weighting needed to address times at which no observations are available. So going into these analyses, do keep that in mind. As we go into the composite analyses, there were a few things I was expecting to see just based off of very initial looks at the data. I was expecting to see temperature decreases and moisture increases since we're affecting that marine air mass that is generally cooler and more moist over inland. And I expected to see a planetary boundary layer height drop as a result of these changes in the thermodynamics. What I have here is the preliminary results of our Houston-wide composite. This composite consists of sea breeze cases from each of the 3 sites with a total of 65 cases making up this composite. An initial look at the figure does show a slight decrease in the PBL heights, a decrease in temperature, and an increase in the water vapor mixing ratio, which is consistent with what I expected to see. To help really visualize these differences, I made some difference plots. And to do so, I found the average potential temperature and water vapor mixing ratio for this 2-hour period before the sea breeze passage. And then I subtracted each post-sea breeze profile by this average, and that led to our difference plots that we have here on the right-hand side. Again, you can more clearly see that after the sea breeze passes, we have a general cooling within that layer and a moistening. Now, if we break this Houston-wide composite down into one of the specific sites, in this case we have CLAMPS2, you can see a little more detail here. Remember, this site, CLAMPS2, is our site that's closest to the coast, and I was initially surprised to see that we have basically no change in the boundary layer heights after the sea breeze passed through, despite seeing a cooling and a moistening of that layer just above the surface. Out of the other 2 sites, this site also experienced the most moistening out of the 4 sites, with an increase in water vapor mixing ratio over 2 grams per kilogram. One thing that I have noticed as well throughout my initial look through and initial inspections of the data is that the effects of the sea breeze can span a wide range of differences, both from case to case, but also from site to site. So to gain a sense of this variability, I created the standard deviation plots for each of the current composites. These plots have all had the same color bar for the temperature and then for the water vapor mixing ratio to help you more easily discern how different each site is. CLAMPS1 has very, very large standard deviations, especially in the temperature, with some of them well over 5. And this indicates that there's a great amount of variability within the sea breeze cases of the temperature, both prior to and after the sea breeze passes. Along those same lines, CLAMPS2 indicates larger standard deviations in the water vapor mixing ratio values for the sea breeze cases, especially right before the sea breeze passes the site. The dashed lines on these plots indicate the PBL height plus and minus 1 standard deviation. And this shows that the PBL heights can vary over 1,000 meters at any certain point in time, again showing a visual depiction of the evidence of the variability amongst the different cases. Just another way to visualize this variability, I have 2 examples here from CLAMPS2. The figure on the left is from July 16th, and a sea breeze passes over the site just before 17 UTC. This case shows very small changes in the PBL heights prior to and after the sea breeze. The sea breeze in this case also occurs before longer time scale thermals develop, which you can see in the bottom panel of the vertical velocity from our lidar. When you compare this case to the panel on the right-hand side from August 18th, there are several differences that are apparent. First and foremost, you can see that there is a difference and a decrease in our planetary boundary layer heights after the sea breeze passes. Cooling and moistening is also more apparent in this case. And the magnitudes in our vertical velocity variances change both in time and the magnitude. This case did occur a couple of hours after the case in July. However, it's still several hours before sunset, and therefore several hours before any sort of transition period might be there. So some of the big key takeaways from the work I've been doing so far is that Houston in general does see a slight cooling and moistening of the PBL after the sea breeze passes. Also, the sea breeze can be variable, both from site to site and from case to case. And there are days where we see almost no variability or almost no effects of the sea breeze or response to the sea breeze, and then days where we see much greater responses to the sea breeze. So for steps moving forward in my project, I want to analyze the synoptic and near surface mean sea level pressure conditions during the tracer campaign using self-organizing maps. Now that I have a general sense of the response to the sea breeze, I want to bend my sea breeze cases in different ways to see if any trends can be teased out. Before the bending can be done though, I do need to refine my composite analyses to account for proper weighting for when we do have data outages. There are still also outstanding questions that I'd like to address as a part of this project, such as how the sea breeze may aid in convection initiation. What causes differences in sea breeze depth, and also what causes differences in the propagation speed of the sea breeze front. Thank you everybody for coming, and to everybody who's given me help and support, and I will take any questions that you may have.
Thank you. Are there any questions for Michelle from the audience? Anybody in the online forum have any question?
I'll ask a question. So going back to those two sea breeze, the comparison of the two CLAMPS 2 cases. There. So it really looks like, especially in the lidar, that that after the sea breeze passage, that you basically start your boundary layer over. I mean, if you look at like 17Z, that looks like how the morning transition from in the lowest 1 kilometer. Whereas when you look at CLAMP the other day, there isn't that like strong difference in kind of ramping up your boundary layer. And I'm wondering what you think. So you mentioned that the one on the left is earlier in the day, but do you think that that's what's preventing the differences from occurring? Because it does look like you do have an initial decrease in your boundary layer height, but then it kind of stops. So
after reviewing some of the radar animations, I think it is more a fact of sometimes it almost appears that the sea breeze front is basically forming right over CLAMPS 2. So it's like you don't have that hard boundary between the two different air masses. So my thought process, especially after seeing some of these animations when it becomes clear as a sea breeze front, is that this specific site is sometimes just in like the perfect place to kind of not have those separations in the air masses. If that makes sense.
Really good talk, Michelle. So I had a quick question. With regard to some of the composites, you were saying like you expected the results that you saw with like increased moisture, decreased temperatures. Were there any results that you've been able to gather where you're kind of like, not confused, but it's opposite compared to what you would have thought, and you're still trying to work through or explain kind of some of those things?
Yeah, CLAMPS2 is kind of falls under that line, because if you look at this specifically with the composite, you see almost no change in the boundary layer heights, especially.
Yeah.
And even the magnitudes of like the temperature change are very small. My thought is, with binning the cases in different ways, I'm hoping I can maybe understand better why we're seeing such variability. For instance, if we have predominantly onshore flow already before the sea breeze front occurs, which does happen quite a lot in Houston, since you're under mostly that anticyclonic condition, that some of this is maybe a result of just different conditions prior to the sea breeze happening.
Gotcha. Thank you.
Can you go back a slide?
Like this way? Or this way?
Backward. Like instead of going forwards, go backwards. It's not changing on ours. So.
Oh, yeah.
Sorry. Maybe go to the sea breeze variability slide. Maybe that wasn't. I thought maybe it was right after this one. Yes.
Okay.
So in looking at these plots, one thing that I noticed was the standard deviation at the SPARC site is close, like relatively consistent until the sea breeze passage, and then the standard deviation really separates. And that's not really a trend that I see in any of the other site, like the CLAMP sites. Do you know why that is, or do you have any ideas of why that is?
I have a partial answer at least. So part of my issue with my composites right now that I was not thinking of until about Friday of last week was the fact that I'm not weighting these properly. So at SPARC specifically, we already only have 12 cases to make this composite, but we also have those last like 4 to 5 profiles have even less data points going into this because there was data outages.
Okay.
So by not weighting this properly, SPARC especially, because there are more intermittent data there than we see at CLAMPS1 and 2, where we have a lot less outages, I need to fix the weighting to see if this trend is actually accurate to what's really happening. Because right now, those last few profiles only have, I think, if I remember right, like 5 out of 12 are available. So, we'll see.
Thank you.
So you're not seeing much of a drop in the boundary layer height in a mean sense. Have you looked at like the individual cases and the intermediate output from the fuzzy logic algorithm to see if you see that boundary layer growth that Josh mentioned in the lower levels? And see if the algorithm's just not quite picking up on the right thing, or if there's multiple things it could pick up on. So like in the aggregates, kind of is what I'm talking about.
The what? I'm
Like
sorry.
in the aggregated plots, are you seeing any signal in the lowest levels?
It's just so variable, especially at CLAMPS2.
Mm-hmm.
There are days where you can see that it's like picking up on what you would expect to see, and then there are days where it's just not. There aren't changes in like the vertical velocity variance, for instance, looks like a normal, uninterrupted CVL.
Yeah.
So it's, I've done some looking in those intermediate plots, but it's just like there's no one size fits all
Sure.
to these. So.
There's a question. Well, Brian Green has his hand raised. I don't know if you want to turn the volume up. You can ask.
Oh my gosh. That was almost bad. Brian, can you ask your question? Apparently I'm not smart enough to do this.
We had that. We'll have to mute one of the computers.
I have, unmuted one. It's,
Yeah, unsound one, not unmute.
yeah.
Yeah, this is, the sound is turned off.
Okay.
Nope, that's not gonna work. He's gonna type the question out. Anybody else have any questions while?
Zoom as well.
This is on, yeah, this is on Zoom. No, 'cause-
While we wait for Brian to type out his question, I have one more maybe suggestion or thought in that you mentioned that you want to look at the synoptic cases and mean sea level pressure. I'm just wondering if early on, if you noticed that the differences at the CLAMPS1 site are related to the background flow, in that you are having a stronger mean wind in those days, so you don't really have a chance for a good land planetary boundary layer to develop at that site, because you're constantly advecting over it and kind of making a more fuzzy boundary layer than what you would on a no flow type of day.
Clamps 1.
At CLAMPS2.
Oh, okay. I was like, clamps 1. So,
I think I have to think through what you just said. The majority of the days are onshore flow already.
So I was just wondering if you've seen, like, maybe on the days where the onshore flow is stronger, that you don't, if maybe those are more the fuzzy days in terms of the sea breeze.
I haven't looked in to see if that's the case or not. That's a good idea to look into it.
in addition to that, there's also the bay breeze that sometimes develops earlier.
Yeah.
Can you comment on how that may influence your results?
The bay breeze complicates everything. There are days in which the bay breeze, it's hard to distinguish, especially at CLAMPS2, whether it's actually the sea breeze or the bay breeze, because it's kind of in that transition between where the bay breeze reaches and where our sea breeze usually ends up. At CLAMPS1, there are also days, about 4 or 5 days, that are impacted by just a bay breeze and not a sea breeze. So I haven't figured out a good way of analyzing those differences, because especially at CLAMPS2, it's not clear which is which on a lot of the days. Because if you watch like the radar animations, for instance, it kind of just becomes one line in boundary.
Okay, so Brian's question. So on the composite CLAMPS profile time series, maybe a slide back, I think from your current slide, could you comment on why the maximum in the heating/cooling and drying/moistening above and below the PBL top does not really reach full strength until an hour after the sea breeze passage?
I am wondering if part of this is because of a bay breeze, like maybe we're getting an initial signal of the bay breeze before the full sea breeze pushes through. I have not teased out why this necessarily is so yet. It's a good question, but I'm guessing that it has to do with almost like a transition from maybe an initial effect of the weaker bay breeze, and then once the sea breeze pushes through, you have that full marine air mass moving over the site.
Any other questions from anybody? If there are no more questions, let's thank Michelle again for her